speaker, who is Roberto, a professor from here, from the University of the Northeast. And he will talk today on the quantum transmission through quantum dot arrays and the magnetic field. Let us welcome him.
Thank you. Well, this presentation, I am going to talk to you about this electronic transmission, particularly through quantum dot arrays and the effects of the magnetic field on such a transmission. Well, just as a reminder, what's the problem, or what's the new properties that arise at the nanoscale when we have a conductor, is that the distance that the electrons travels is comparable to the size of the system. So, in principle, you don't have so much diffusive transport, which means that you don't have too many scattering events between the electrons and the ions or the crystalline lattice. So, principally, the wave nature of the electron has to be taken into account, which means that we have to think in a different way for considering the quantum transport or the electronic transport through this kind of system. Well, it is just a reminder, and also emphasizing the use, or at least the proposal to use, to mimic the nature to produce new kind of system. In this case, for electronics, the purpose of molecular electronics is to use molecules for different purposes in the circuit, like wires or switchers or rectifiers or things like that. This is supposed to be the electronics of the future, maybe in the next 10 or more years. But currently, people is working on other systems, not only molecular system, but the so-called mesoscopic systems. Well, just a fast reminder of these approaches, because I'm going to use some of these things. One theoretical approach is to use scattering theory of electron transport, which means that the electron has to travel through a barrier and then has to use its wave properties to pass through the barrier, just like light wave pass through a material. So we have an incident wave, reflected and transmitted waves. How do we understand conductance from transmission? We have to think that the electrons are waves that have to pass through the system, and the system has a size or the same order of the wavelength of the electrons, or even typical wavelength, for example, the scattering wavelength or the occurrence wavelength. So conductance at this scale is basically a process of wave propagation. Well, in this case, the current at a low temperature is characterized by this transmission coefficient, which is the usual coefficient transmission that we use to calculate in elementary quantum mechanics when we consider a wave passing through a square barrier, for example. This allows to define the differential conductance as a derivative of the current with respect to the bias voltage. as a numbers formula. This typically it describes the conductance of electrons in a coherent regime. This is basically the same. We have this. This is the quantum of resistance, which is a magnitude characteristic that depends on the Planck constant and the electron charge. So two fundamental constants. At finite temperatures, the current is described by this interval, which represents T. E is the transmission for an electron with energy E. FL and FR are the occupancy of the left and right electrons with an energy E, and you have to integrate summing over all the energies. So this is the total current, and the difference, the minus sign here, represents the difference between the two currents. Well, now what happens if we apply the magnetic field? This magnetic field acting on the electrons produce an effect, a particular effect known as the Carnot-Bond effect, which has the particularly has the particular property that even when we have a zero magnetic field, the vector potential produces observable consequences. If we remember this ideal situation of two slits, one electron that comes to both slits because it behaves as a wave, we can attribute a path 1 to the electron passing through the first slit, and path 2 for the electron passing through the second slit. But we have a pattern of interference that can be observed here with this screen. And we have here a solenoid. The solenoid produces a magnetic field inside it, but there is no magnetic field, of course, outside the solenoid. But there is a vector potential. And this vector potential, it is known to produce a change in the phase, and so there is a final interference pattern, not only because of the quantum nature of the electron, but also because of this dephasing produced by the vector potential. So we have two sources of interference. One is typically quantum, well, both are quantum in character, but one is proper of the wave description of the electrons, and the second is because of this vector potential acting on the trajectory. Well, this can be produced at nanoscale, and has been fabricated. This is a device. This is a real image of the device used by Thomasin and co-workers in 2007. It is formed by it's a heterostructure of two semiconductors. One is this thin containing film on the top, and these bright lines are top gates, or gates for producing or controlling the motion of the electrons in this device. Here, these two dots are the quantum dots, and this ring are the trajectories of the electrons from source to drain. A quantum dot is also called an artificial atom, because it is a region where confined electrons. Typically, when it is two-dimensional, like in this case, typically this confinement potential is due to electrostatic gates, like in this case, but it could also be in a three-dimensional confining potential, for example, in nanoparticles or nanoclusters. Well, in this case, we have at the interface of the heterostructure, we have a two-dimensional electron gas that is finally confined with these plunger gates or these top gates, source and drain top gates. So you can apply voltages to, for example, low open channel between the two dots, or to open a channel between one dot and a drain, or one dot and the source. So you can control all the channels between the dots and the electrodes, source and drain. We call this then a quantum dot molecule because it mimics the diatomic molecule formed by these two artificial atoms. So we say that this artificial molecule is embedded in the interferometer. Perpendicularly to the interface, there is a magnetic field, so you can test the Herner bomb in this nanoscale device. Well, some of the measurements that IN was taken on this device are these curves where you have the conductance as a function of the magnetic field for two different plunger gates. The upper one corresponds to the 125 millivolts for the top plunger gate, while the lower one corresponds to 150 millivolts. This difference in this bias voltage applied on the top gates produce that you can open or close the connection between the two quantum dots. When you have this 125, the quantum dots are connected, so you have a real artificial molecule, and when you have this voltage, the quantum dots are isolated. So you can open or close this channel between the two dots. The figure, this figure corresponds to the Fourier transform of this curve, where you can see that there are two particular frequencies in the magnetic field corresponding to typically 20 and 40 millitesla. These are called the big orbit and the small orbit because they are supposed here, we are proposed in this paper to take into account the big orbit correspond to this path, this circle without the channel between the two quantum dots, and they call small orbit at the half of the big orbit. So you have two different areas with the same magnetic field. You have two different fluxes. One is twice the other one. That's the reason that you have these two periods, 20 and 40 milliters. The big orbit can be seen here also. But in this picture you have the conductance, actually the ninth root of the conductance in terms of the plunger gates 1 and 2. These plunger gates are these two here that can control the occupancy of the electrons, how many electrons I have in each quantum dot. So these plunger gates allows you to keep constant the number of the electrons, for example, in one quantum dot, and allowing to change the number of electrons in the other one. So they can be varied independently. So this is the result of the measurements for these conductance. The reason of using the ninth power of the conductance is simply to emphasize these lines. So like using a very non-linear palette of colors to represent this conductance. So essentially it's the conductance in terms of these two voltages which allows to control the quantity independently. These two figures correspond to the traces, green and blue one. The green trace, we have up to 6 electrons, which are added one by one, while the number of electrons in the quantum dot 2 is constant, and the other way around for the blue trace. In both cases, the analysis of the results shows, in this case, it's better seen than in this other case. But in both cases, one can see that there is a periodic conductance modulation with a period in the magnetic field of about 20 millimeters. So, in fact, this corresponds to the so-called big orbit. For the small orbit, the different Klunger gates allows to open this channel, or actually to pinch it off. So one has only half of the circle, which should be the small orbit, and again one can measure the conductance as a function of the two Klunger gates. Now the current as a function of the magnetic field, or the voltage as a function of the magnetic field, shows that one has these peaks that after Fourier transforming, you can see that there is a period, maybe a Hardy-Markov period of 40 millimeters. In this case, the two quantum dots are not symmetrical. The device is asymmetrical for both, because, for example, one of the quantum dots, the upper quantum dot, has 2 terminals, while the lower quantum dot has 3 terminals. So the behavior should be different. Well, another thing that can be measured is the so-called final phase, which in this case is represented by these curves corresponding to the conductance as a function of one of the Klunger gates, in this case VPG1. And in these curves, one see these peaks that, if you look closer, are asymmetrical peaks. The final effect is known from the 60s, and it is an effect that arises when you have a continuum interacting with a localized state. It was first considered when treating problems in atomic and molecular collisions, when you have a projectile having a continuous of energy and impinging on a target with discrete of energies. So you have a localized state and a continuous state interacting with each other. So the typical cross-section in that case has this kind of peaks, asymmetrical peaks, what's called a funnel after him. But not only there, but in many other processes and many other areas of physics has arisen this funnel effect, and it's nice that it has also measured in this kind of system at nanoscale or nanoscale systems. So this shows the signature of continuous interacting with a discrete state. Here is another experiment. In this case, it's by other people in 2006, where they use this is a photography of this is a quantum ring and this is a quantum dot. They are connected with each other, and the connection can be turned on or off through these gates, these top gates here. And here also there is the signature of these Hartmann oscillations in the conductance as a function of the magnetic field. In this case, the period is 61 milli-Tesla. So these final and Hartmann effects are closely related in this kind of system involving rings or quantum dots. Well, we theoretically have studied this kind of system through this model. So I will describe now the model that we have used. We consider these 4 sites, which are our quantum dots, and they are described by Hamiltonian, including this T, T12, T23, T34, T41, and V, which connects 2 and 4. The T's and the V's are the interaction between pairs of quantum dots. There are 2 quantum dots, in this case 1 and 2, that are connected also to 2 electrons, left and right. In this case, 1 and 3 are connected to both electrons. So we have considered here 2 different configurations. Actually, this configuration is the one that corresponds to the experiments. But we have calculated both to see the difference and to see whether this another configuration could represent any other have any other functionality. The motivation for using this kind of system is, on one hand, is to, of course, understand the transmission, the electron transmission on this scale, where the electron has to be considered not like particles, but like waves. And on the other hand, is to produce new devices that, for example, can be controlled by a magnetic field. If I have a magnetic field that produces effects on the conductance, on the transmission, I can turn a knob to change the magnetic field, and then I should produce changes in the current. In this case, the device could also be a device to measure something, to measure magnetic fields, because if I have a current between the electrons, any fluctuation in the magnetic field would produce effects on the current. So it could be a magnetometer also. Well, the description is basically that the electrons are coherent, the transport is coherent, so the electron doesn't lose the coherence due to, for example, interaction with the vibrational degrees of freedom. So basically there are no effects due to temperature. It's hardly seen here, but we have a couple of D and D dagger and an exponential in the phase, which means that we, if we have one electron in dot 1, I can annihilate it create it at dot 2, and that represents a jump or a hopping from site 1 to site 2. And you have to pay a phase if you have a magnetic field there. This phase from going to from site 1 to site 2 is the Hartmann effect. So the change of phase is directly including a hardware bond in the model. Well, this the second part, the second term is the Hamiltonian of the leads, which is basically the same electron coherence, but this K is a continuous index, so we have a continuous here, while for the dot we are supposing that we have single level quantum dots. That means that each quantum dot is represented by with a single level, a single orbital. So we have a discrete in the quantum dot and a continuum in the leads. That should be enough to catch the basic picture of the final effect. This is the interaction between both the dots and the leads. Well, the current then is, as I said before, is obtained from the Landauer's equation. For this equation, the important thing is to get this transmission. The transmission is obtained from Green's function, advanced and retarded, and these gamma functions, which represent the connections between the isolated device with the leads. These Green functions, in due time, are obtained from other Green functions, G Green functions, the G small g. The small g are the isolated device Green function, and the capital G is the couplet to the lead Green functions. So, by studying the isolated device, I could obtain the coupled device, then obtain the probability of transmission through the whole device, and finally the current taking into account the occupancy of the leads. To have an idea of how do I get this small g, they are obtained, for example, in this spectral representation, which means that I need to know the wave functions, all the spectra of the isolated device, and its energy. So we have to solve the complete system, isolated system, to obtain the isolated device Green function. Well, this I will not enter into details, but we can say that the condition for the onset of resonances, these resonances are have the signature of those peaks, asymmetric peaks in the case of final effect, are determined by the poles of the Green functions. This G1n means that is the element 1n of the Green function, where 1 is one of the sides connected to the left electron, and n is the side connected to the right electron. That is, for our two configurations, n should be 3. So the poles of this Green function determine the probability of transmission. And at these poles, we have fine transmission and sometimes even perfect transmission. That means that you have 100% of your electrons impinging here with the right energy, and you have a complete transmission on the other side. On the other hand, if you look at the poles of the G11 and GNN, we have series of transmissions with what we call anti-resonances. So we have no transmission at all at the energies marked by the poles of these two Green functions. So studying the structure, the electronic structure of the device, of the isolated device, one can in principle say whether you will have transmission or not. But the reason is that in this case the Green function near the poles can be approximated as a number, the residue, and the difference of the variable, the energy, and the eigenenergy of the system. So when I have, when E is close to one of the eigenenergies, I have a divergency here that finally produce a finite transmission in the device. Well, another point here is that if you have waves that are going through two different paths, it's like when in the ideal experiment we have two slits where the electron pass through, and you don't have actually trajectories, but you have a pattern of interference. Well, at this scale, that's what happens. So, as a way to recover some idea of the pathways for the electron, we employ a partitioning technique. This partitioning technique consists in using a projector. This Hamiltonian, which is it's a matrix of 4 by 4, because we have in this case 4 quantum dots, is blocked in 4 blocks of Hamiltonians or matrices of 2 by 2. So in this corner we have the parts of the Hamiltonian depending only on size 1 and size n. So this corner, this block, corresponds to the part of the Hamiltonian that describe the two sides that are linked to the leads. This part, on the other hand, corresponds to the other two sides which are not coupled to the leads. And the U describes the interaction between these two parts. So in the configuration where I have side 1 and side 3 connected to the leads left and right, P corresponds to sides 1 and 3, and Q corresponds to sides 2 and 4. And U describes the connections between these two subspaces. So the problem is to get this green function, and using this partitioning, one can write a matrix equation like this, where we have here the energies of the system and these new quantities which are called self-energies. And these self-energies describe the influence of the Q part on the P part. So the self-energy describes the influence of the sides which are not connected to the leads on the pair of sides connected to the leads. It's just it's a mathematical trick, in fact, but it is convenient to recover the idea that each one of these describes a path for the electron. So you can say that the electron goes through for example, path 1, 2, 3. This sequence of quantum dots describes a path, or 1, 4, 3 is another path, or you can have a path passing through the quantum dot molecule, for example, 1, 2, 4, 3, and going to the right of the tree. So we have in this case 4 different paths, which correspond simply to the application of this partitioning technique. So it's a mathematical trick, but it's good to have some intuition of the pathways for the system. Now, what's about if I apply a magnetic field for this, for example, this asymmetric interferometer, where we have D equal to 0, so the quantum dots are not connected with each other. Only we have 2 paths, the upper path and the lower path. This is the case, the transmission as a function of the energy of the electron when we don't have a magnetic field for the 2 different configurations. The continuous line, the solid line, corresponds to the configuration where the symmetric configuration, where the sides 1 and 3 are connected to the leads, and the dotted line corresponds to the other configuration where 1 and 2 are connected to the leads. So you see that the two configurations have very different properties, very different transmission. At zero energy, which corresponds to the Fermi energy of the electrons. In one case, I have maximum of transmission, actually 1, so 100% of transmission of the electrons, while in the other configuration I have 0. I don't have transmission again. While when I apply a magnetic field, this is the flux, the quarter of the quantum of flux, there is a important change in the behavior, because, for example, for the solid line, the 1-3 connection, the zero energy, which was generate, there were two peaks here overlapped. Now the magnetic field breaks such a degeneracy. So we have 4 peaks corresponding with the 4 energies of the eigenenergies of the system. And on the other hand, the magnetic field also eliminates the anti-resonance. There is no 0 at all, but there is a high transmission now. So a magnetic field can produce a remarkable change in the transmission properties of the device for both configurations. This is for 0.5 of the quantum of flux, and this is 0.48. So they are very close to each other. But you can see that also this small change in the magnetic field applied change this for the 1-2 configuration, change this, which is a peak, in an anti-resonance. So it could be a very sensitive manner to measure changes in the magnetic field. Well, not only that, but you can also use the different parameters of the system to produce a tuning of the transmission when there is a molecular coupling. So this B is not 0. Actually, these 3 figures compare B equal to -1, 0, or 1. So in this case, we don't have a molecule, but two quantum dots individually, and in these 2 cases, the coupling is opposite to each other. The curves that we see here, let me see in more detail here. The solid line represents the transmission around the complete system. So this solid line, this sort of yellow color, is the transmission without magnetic field. The black one, dashed black one, is the same for the same values of the parameters, but with a magnetic field. With a small magnetic field, actually is 0.1 the quantum of flux. But as you can see, this is in this instance, you see the same but magnified. You see that the main effect of the magnetic field is to manipulate this anti-resonance. So without magnetic field, you have 0 transmission of this energy, and you have a final transmission now when you have magnetic field. The other 2 curves corresponds to the device when you, for example, put T12 and T23 equal to 0. So in fact, you only have an arm of the interferometer. So the electrons goes, for example, to the lower arm, 1, 4, 3 to the right. But you also have this quantum dot laterally coupled to such an arm. So it's like a 3-side chain with a laterally coupled quantum dot. That corresponds to this So it's to this red or pink curve. And the blue one corresponds to doing the same, but with t equal to 0 here, between 1 and 4, and between 4 and 3. So the electrons goes through the upper arm with the side 4 as a lateral applet. What you see there is that basically the yellow curve corresponding to the whole device is quite similar, for example, to this blue curve corresponding to only one of the branches. That depends on the value of B. You can see in the previous figures. You see here that the continuous line case here, or in the middle, depending on the value of B. So this interdot coupling can be used to tune the anti-resonance, or to choose the energy at which I want the electron to have transmission zero. So the high tunability of the system allows you to produce resonances or anti-resonance anti-wave. Well, this is another way to see the transmission in this configuration. Now the 1 and 2 connection, because 1 is connected to the left and 2 is connected to the right. So this is not a symmetric configuration for the system. And we have here the logarithm of the transmission, the probability of transmission, in terms of the flux in the vertical axis and the energy in the horizontal axis. So you see these bright lines representing the pairs of flux and energy that has a transmission almost 100%. This bright line represents the transmission, the pairs of flux and energy that gives 100% transmission. On the contrary, these dark regions correspond to low or zero transmissions. This is when you see a sample of this here in a closer view, you can see that you have a dark region and really close to it bright region. So you have peaks on anti-resonance very close to each other, and that is the signature of the final effect. This final effect is this kind of peaks where you see the transmission as a function of the energy at some peaks go to 1 and then goes fast to 1 and even faster goes to 0 or to a very low value. So you have a resonance and anti-resonance very close to each other. That is the final effect in a device like this. In this case, this is an asymmetric interferometer because the upper arm T12 and T23 has strength 0.2 in arbitrary units in this case, and the lower arm has 1. So it is much more probable for the electron to go through the lower arm. Well, this is the case when we have the energies at the quantum dots 2 and 4 different. In A2 we have 2 units, and in A2 we have 4 units. In this case, there is no coupling between the quantum dots, and the arms are also asymmetric. And we have something like this. We have this resonance or anti-resonance. Particularly, this is for field, magnetic field equal to 0. What if we turn the magnetic field on so that the flux is a quarter of the quantum of flux? Then you see that this peak that was before was a final peak with a resonance and anti-resonance. With the magnetic field, the anti-resonance is suppressed. So you only have peaks of resonance with 100% probability to transmit at these energies. If I take now the magnetic field to have the quantum flux, again I have an asymmetric profile here in the this energy, almost in the same energy as before, which corresponds basically to the side coupling quantum dot. This is almost a side coupling quantum dot because the lower arm is much more stronger than the upper arm. But in this case, you see that the anti-resonance is at the left. That means at lower energies than the peak of resonance. Sorry, in this case, first I have, when I go in energy, in increasing energies, first I have the anti-resonance and then the resonance. And if you recall, at phi equal to 0, we have the opposite order. So you can change, not only you can suppress the anti-resonance, but you can also change the order of the resonance and anti-resonance by applying magnetic field and tying the parameters of the body, which are almost the same as the parameters of the experiments. So finally, we have considered here this configuration. These to the right are the configurations 1, 3, quantum dot 1, quantum 2, quantum dot 3 connected to the leads, and this is the 1, 2 connection. So this is for B equal to 0 in both cases, B equal to 0.5, B equal to 0, B equal to 1, and in this case we have disconnected two quantum dots, quantum dot 2 and 3 as in the experiment, to see the effects on the transmittance. This is the transmission as function of the flux in the vertical scale and the energy in the horizontal scale. If you see here this comparison between the upper panel and the lower panel, the upper panel, a very definite period can be seen, which is exactly half of the period in the lower panel. So you have a change in the period by a factor of 2 by simply changing the connections which correspond to the big orbits and the low orbits. In between, when you turn the connection between the quantum dots, so you have a molecule, gradually you go from here to here, changing the patterns, but always having a period corresponding basically to the small orbits. That happens in both cases. So actually the change in the configurations, because we are not putting here any area for the ring, the change in the configuration is responsible for changing the period by a factor of 2. Well, in summary, basically I wanted to show how a real device can be studied with this kind of models, where one can use the different parameters of the model to account for the different effects, the final and the Halo effects, and how these the changes in these parameters can produce important or remarkable changes in the transmission of the quantum dots. Finally, Somehow, with the formalism of partition techniques, one can decompose the transmission in terms of pathways in order to recover some of the intuition of trajectories, which is not real in the most work. Thank you.